in this case, what we have to do is to increase the redundancy. And so that's a trade-off between general error rate and the redundancy that you have to add to protect. Okay? Now, so Reed-Solomon code is a generalization of Hamming code. So instead of working on the fields of 0 and 1, it works on the field of integers. Okay? So, and it offers better protections. Okay? So basically, for Reed-Solomon code, what happens is you still receive your packet, and it depends on your the behavior of the channel. You decide to have more or less protections, or it depends on what type of data that you are dealing with. For example, for all the motion vectors, you might protect it more than the residue. Okay, so as the designer, we can have all those things available to us. Now, let me bypass this and talk about error concealment. So that is retransmission and channel code allow us to get lossless protections. Okay, within a certain limit, of course, right? Within the channel capacity limit, within the channel error limit, with the combinations of FEC, forward error corrections, and retransmission, we will be able to deal with the losses in our communication channels, right? But then concealment is another technique that allows you to boost up the communication rate, okay? And because you allow errors to appear, but you will try to go back and correct the error using some kind of interpolation techniques. Okay, so it's conceal means you want to hide the error. Okay, so an example would be this. You can use spatial interpolation. Okay, now I strongly recommend you. I think we're trying to do this in our MATLAB exercise, but even if we don't assign this problem to you, if you're interested, I strongly recommend you to try this. It is very easy to simulate this problem. Okay? What you want to do is to take an image, and you divide an image into 8 by 8 blocks. Okay? 8 by 8 blocks, because that's our DCT size, right? Okay? And then you make sure that you alternatively lose blocks. You don't lose 2 consecutive blocks, okay? Because losing 2 guys make your interpolation very difficult. Okay? But suppose that you're here. You're missing this blocks right by Leonard's eyes. Okay? What you want to do is to interpolate this black blocks from 1, 2, 3, 4, 5, 6, 7, 8 neighboring blocks.
Average.
Yeah, you can do simple averaging and see what happens. Okay? You can, believe me, you can just do simple averaging and you're going to be able to get, maybe not quite here, but pretty close, 30-something dB. Okay? 30-something dB. So this is, as you can see, I'm throwing a quarter of my information away. Right? I'm throwing a quarter, 25% of my information away. And I'm still okay. Okay? So nobody knows. If there are 30 frames of Lambda passing by you, you wouldn't even know that you actually have a lot of errors. This is a lot of errors. Okay? So this is the power of error concealment. Okay? If we do packetization right. So these, see, I have a regular loss because I do packetization right. I make sure that there's no neighboring blocks grouped together into one packet. Okay? So I might lose 1 out of 4 packets. Suppose I have 4 packets covering this Lambda image, okay? Then I'm losing 1 out of 4. And I'm still okay. Okay? So that's spatial concealment. Temporal concealment for video is even more powerful. What you did is, you go to the previous frame, and hopefully you have the motion vectors. Okay? If you have the motion vectors, you go to the previous frame, you pull out the correct block, and you just fill in the blank. If If you don't have the motion vectors, then what should you do? Just copy the previous plot with 0, 0 motion vector. You have a very good chance that it's going to be okay. You have a very good chance that it will be okay. The probability is with us, not against us in that case. A lot of times, if you do statistical study of the motion vectors in regular video streams, guess what motion vectors is most common? 0, 0. Or the copy, okay, is most common. Then after that, the small one, 1, 0, 0, 1, 1, 1. Those are the type of motion vectors that's very popular. Okay, so you can use that. You can make a very intelligent guess on what is missing. Go to the previous frame, copy it over, all that. Okay, so that's temporal concealment. So another type of you can get slightly smarter. Okay, suppose you lose this plot, and you lose everything. You lose the residue as well as the motion vectors. What you can do is take a look at the 3 motion vectors here. Okay, and say, well, if I'm here, I should be moving with respect to these guys. So maybe I take the median of these 3, or I take the average of these 3 or something. Okay, and I call that my motion vectors. And then I go to the previous frame. Based on that motion vectors, I pull the plot over, fill in the blank. Okay, so that's another type of temporal concealment techniques. Okay. So maybe let's stop here for a break. Okay, quick break, and then we go back. Where can these slides? Yes. Concealment is considered a subset of post-processing technique. Okay. So concealment is a technique. Post-processing means you decode and then you do some processing after you decode. Okay. So certainly that concealment fits in that case, right? You decode and then you determine where the error is, and then you try to eliminate the error, so interpolate the error as well. So there are motion compensated temporal predictions that we just talked about that, right? That's a part of it. That's temporal concealment. There's maximally smooth recovery, which is a part of spatial concealment, right? Interpolation in time. But you want to do it in such a way that it exploit the correlation both in time and in frequency, and you want to make sure that the edges stay sharp. Okay, so it's just a particular case of interpolation, and there's fancier techniques called projection onto convex sets. It's a type of iterative, frame-based iterative approach that do smoothing and replacement of data. Okay, that's you can do frequency domain interpolation. For example, you can interpolate the DCT transition from the data. That's another way of doing things. And you can do recovery of coding modes and motion vectors, like predict from the neighbor or the previous frames. Now, in video coding, we have to worry about 2 things. We don't want loss of synchronization. Okay, the decoder doesn't know what bits correspond to what parameters, and that is very troublesome. Okay, if you don't know what bits belong to what parameters, you will decode the parameters incorrectly, and that will lead to all kinds of problems. Okay, and then error propagation means the decoder state is different from the encoder state, leading to a mismatch. Okay, and then error will propagate. Okay, so this is loss of synchronization mean. Okay, any error